In this module, I want to talk about the scientific process. What is science, and what is the scientific process? And how does that fit into what data science is, and how is this all connected? So let's start simple. So the scientific process has been invented thousands of years ago, literally. In fact, the people credit the Babylonians for describing that process already. And it basically has two major building blocks. The one building block is the experiment. So the experiment creates observations. We already talked about observations before, as we say observations are, for us, data. So those observations are then put, usually traditionally, into a human brain. As the human brain absorbs these observations, it starts thinking, and as it thinks, it comes up with a theory. Why do we come up with a theory? Well, we want to learn something, we want to understand something, and what this means is that we generalize from these observations to be able to predict future observations, right? So we can predict the experiment. For example, if I watch 5 different objects falling from some height to some lower height, it will be easy for me to say, well, the 6th object will probably also be affected by gravity, right? So that would be a typically observation and prediction. So now also it's important that whatever theory we make, experiments actually need to validate that prediction, okay? So now the scientific process, which I'm going to make it scientific process, is, as I said, not new. And in fact, anything that calls itself science, whether it's political science or computer science, should obey that scientific process. In fact, in computer science, it's almost quite clear that we do, because what we do is we write some piece of code, and then we run it, and we see, oops, there's a bug, it doesn't work, and then we need to see where the bug is, and as we predict, and so on and so forth. And ultimately, when our code is perfect, we have something that we can predictively say will, so that our program will be our theory and will predict the outcome. For example, we could create a program that adds 2 numbers, and then we can say, well, for whatever number you put in there within a range, it'll add these 2 numbers, right? And then we should observe that this is true for all the numbers we ever put in there, and then we finally approach through these cycles something we should call the truth. So now in modern times, many people have proposed additions to the scientific process, and that's mostly to do with the invention of a very particular machine that would be the computer. And what happened first when we started to introduce computers into science is that they were mostly built as an extension of theory. So what would happen is we could use a computer to basically shortcut some experiments. And this would be done by adding the following. We would do simulations. So a simulation will basically give us observations, right, back to the theory, and also the theory will actually feed the observations, the simulations, with predictions. And that we can use to shortcut experiments, right? So for example, sometimes experiments are very expensive or also dangerous, right? Think about, for example, explosives or biological growth of bacteria or viruses. If you can simulate this first before we actually try something, it could help us reduce some risk. So simulations have been around for a long time. But what's newer, especially in the recent decades, is another extension of the scientific process, and that is machine learning. Machine learning actually tries to do something else. Machine learning fits on the right side of this diagram. What machine learning does is it also provides prediction and experiments, but in the other way. So funnily enough, we will put in observations into the machine learning, and then the machine learning will create predictions. So now, for anybody who's ever worked with machine learning, sometimes we are very okay with the predictions just doing its thing and not really knowing why the predictions come out. But if we were scientific about it, we want to know exactly why some predictions are made or why they're not made. Because if you really think about it, when we do theory, we have a very clear way of validating that something fits this theory or not, right? So the whole field of math has come up with a whole set of tools of how to prove things using logic, and also how to count things, how to make sure basically we stay within our bounds. So for machine learning, things can be quite complicated. We can have 100 millions of parameters describing the observations of some experiment, and indeed maybe coming up with accurate predictions. But as a human, we don't even have any time to even look at, let's say, hundreds of millions of parameters. So there's a very important principle that we need to add to all of the process, which has been there also for a long time. And that's the principle of Occam's razor, okay? So Occam's razor says, Occam's razor says, the prediction or theory with the least amount of parameters is the one we should favor. This is, we need to figure out how many parameters we need minimally to do the same prediction. And this is going to be another module of how to do this. But for now, we just want to say this is the scientific process. So now that we have the scientific process and we know what science is, we can ask ourselves, what is data science? So for me, all the sciences are connected. For example, if you look at the traditional sciences, we'll have something like that physics implies chemistry implies biology, right? What does this imply means? That's actually meant as a logical implication. This means if you have a biological result that somehow contradicts chemistry, it's most likely not going to be accepted as a result. Or if you have a chemistry result that somehow doesn't really obey physics, then it won't be accepted as a chemistry result. And in similar ways, physics and math work together to do to make sure we can be consistent. However, I would draw a line here, and I would say that physics, chemistry, and biology are called sciences because they obey the scientific process. And math usually doesn't deal with empirical experiments, with very few exceptions, doesn't deal with empirical experiments and observation. It usually mostly helps us give us tools for the theory. And that is that math actually becomes the school of sorts, right? This is mostly the theory part. And obviously, you know, the chain can go left. For example, you could go philosophy. So the field of computer science, for example, was traditionally split into two, right? So we have, for example, that the engineering part of computer science was definitely part of physics. So when you build CPUs or build circuits, it's a very physical process. Though the theory of computer science, building algorithms, is traditionally part of math. So pretty much it's a CS theory. Right? Pretty much you can argue about machines and computation without obeying the laws of physics. It's mostly, it has to be correct with math. So now data science as a science, for me, would have to position itself into the right realm, right? And therefore is for me something that will come out of engineering and will be probably the physics and the engineering of information. So I would call data science a science because we do experiments and we have observations, and so if data science deals a lot with this part of the modeling, machine learning of data, then it basically becomes obviously a child of math, but it also becomes a child of physics and engineering. As such, we need to understand the properties of data and informations and how they pertain to algorithms.